So, starting chapter 2, we're going to start our discussion in chapter 2 with talking about angles. So if you remember way back to your geometry course, in that geometry course we primarily measured angles using what unit? Degrees, right? And most of us, I trust, are very comfortable talking about angles measured in degrees and understanding what that kind of means. There are many different other ways to measure an angle. The other additional angle measurement that we're going to be using in this class is called a radian. So let's define what we mean by that. So if we have a central angle, we can measure these in radians. So we say that a central angle has a measure of 1 radian if it intercepts an arc with the same length as a radius, or as the radius, I should say. So when we say central angle, what we're talking about is a circle with some angle whose vertex is at the center of the circle and whose arms intercept the exterior of the circle. So let's say we have this central angle ABC. We say the measure of angle ABC equals 1 radian if segment AB, which is our radius, is congruent to the arc AC, and the symbol we use to denote an arc, we give it this like curvy hat, is the way we did that in geometry to show that we're talking about an arc as opposed to a segment. And while that description is nice and it's technical and you can prove things with it because it's very specific, it's not very intuitive for us. Oh yeah, we're going to prove stuff in this course. That's a ways away yet, so take a deep breath. All right. All right. The takeaway here is that what we're doing is we're using this arc length essentially as our measurement for an angle, right? That's basically what a radian is. It's imagining if I take this angle and I embed it into a circle of a certain size, the arc length that's intercepted by that angle is the same as my measurement for the angle. That's basically what we're saying when we use a radian. So we've introduced this new unit of measurement for an angle called a radian. We had an existing unit of measurement called degrees. When we have two units of measurement, the first thing we want is a way to convert in between them, right? Just like if you were measuring things in feet and measuring things in meters, you'd like a way to go back and forth between feet and meters, right? So what we want to do next is create a conversion factor that allow us to convert from degrees to radians. To do that, we're going to look at this specific situation. So I'm going to take a circle here with a radius of 1 We have a special name for a circle whose radius is 1. It's called a unit circle because its radius is 1 unit. And a unit circle will play a big part later on in this course. But for right now, I just want to touch on the name, and that's why it's called a unit circle. So the angle that we're going to be using inside this unit circle is going to be a straight angle. Hi. Juliana, it's for you. It's not enough trouble. It's from campus ministry. All right. So, what is the angle measure here in degrees for this angle? 180 degrees, right? Everybody's happy with that? What is this arc length here going to be? Pi. Very good. So you got that very quickly. How did this person get pi? I missed who said it so quickly. Was it Adam? Good job. We know that the circumference of a circle is 2 pi r. So in our case, r is 1. So the circumference of the entire circle is 2 pi. It stands to reason we're looking at the circumference of half a circle, which is pi. So what we can say then is 180 degrees is equal to pi radians. And that's our conversion factor. Knowing this, it's going to allow us to go back and forth between degrees to radians or radians back to degrees. So let's do a couple of examples of that just to make sure that we have that concept down. So let's say we want to convert 90 degrees to radians. So the way that we're going to do this is just like you would have done in your science class or chemistry class when you did unit conversions there. You're going to start with the quantity that you know, and then you're going to multiply it by a conversion factor. So our conversion factor is that 180 degrees is equal to pi radians. Where does the 180 degrees need to go in this fraction? In the numerator or the denominator? Denominator. Very good. Remember that when we set up these ratios, the units should be diagonal from each other. Since 90 degrees is in the numerator, because we have 90 degrees over 1, the 180 degrees should be in the denominator, which means that we'd have pi radians in the numerator. When I multiply that, then I have 90 pi over 180. And 90 over 180 reduces, and we're left with just pi over 2 radians. Now, oftentimes, we're going to write our radians in terms of pi, especially in a case like this where the fraction is very convenient. Could we also write pi over 2 as a decimal? Sure, but oftentimes if we can write our radians in terms of pi, we choose to do that because it's exact. What would I have to do if I wrote this as a decimal? I have to round it, right? Because pi is, that decimal never ends. So if I was to calculate pi over 2, I'd have to round it and give an approximation rather than the exact answer. But it's not incorrect to write pi over 2 as a decimal. We just typically wouldn't do that. So let's say we wanted to convert 152 degrees into radians. So So we'll start with what we know, which is 152. And what do I need to multiply 152 by to get an answer in radians? It's not a trick question. Pi over 180. Same as before. So I get 152 over 180. And here, the reducing is much less nice, right? We could still reduce this a little bit and represent this as a fraction in terms of pi, but we could also type this into our calculator and represent it as a decimal. So if I were to do that, I think the easiest way to do this is just use the fraction command on my calculator. So if I press alpha and y equals, I can just type in 152 pi over 180. And when I do that, I get 2.653 approximately. Everybody cool with that? Yeah. And notice here that in terms of writing a unit after that, oftentimes we'll write like radians or RAD, and sometimes when it's clear from context what we're talking about is an angle in radians, we won't even write that. We'll just write like pi over 2, like theta equals pi over 2 or something, because it's clear that theta is an angle. And if we're representing our angle in terms of pi's, that we're talking about an angle measured in radians. Ben? Yeah, there's not a unit or a symbol per se. I'll write RAD for a while, but eventually it'll be clear that when I'm talking about radians versus degrees, and we'll just stop writing anything at all. But there is no unit really attached to a radian. Everybody okay with that? Again, and the reason there's no unit is because what a radian really is it's an arc length, and the circle we're building the radian from has a unit of 1. It's not 1 centimeter or 1 inch, it's just 1, where there's no unit attached to the radius of the circle, so there's no unit attached to that arc length, hence there's no unit attached to radian. What if we want to go the other direction, and we want to convert some measurement in radians to degrees? So here in this question, even if I had left out the word radian here, it would be clear, because we've written something in terms of pi. If I'm asking you to convert this to degrees, that what we're talking about is an angle measurement in radians. Everybody agree with that? So just like before, I'm going to start with the measurement that I know, and I'm going to multiply this by a conversion factor. What conversion factor am I going to use here? (180 over pi). So if I do that, I get 360 pi over 5 pi, which reduces down to 72 degrees. Everybody okay there? Notice that the conversion factor flipped. It's easy to remember, though, because I know those pi's need to cancel out. So I just need to make sure that they're on opposite parts of my fraction. Everybody cool with that? Should be pretty easy. But we don't always need to represent radians in terms of pi. There's nothing wrong with representing radians as a decimal. So let's say we had 1.6 radians and I want to convert this to degrees. Nothing much changes. Other than I get this 288 over pi, and since we wrote our measurement for radians as a decimal, we're going to write our angle here as a decimal. It's really non-standard to represent an angle in degrees in terms of pi, even though if you wrote 288 over pi degrees, like technically that's correct, but nobody would ever write that measurement that way. They'd convert that into a decimal. Everyone okay with this idea? Should be pretty familiar feeling, right? Nothing complicated going on here. What's the big takeaway? What's the thing that we want to remember from this? That 180 degrees is pi radians. That's the big takeaway. So if a central angle theta, this symbol here, is the Greek letter theta, it's basically just a zero with a dash through the middle. Typically in trigonometry, the convention is that we'll name our angle variables using Greek letters. We name like the vertices of our shape using letters, or we label points with capital letters. And we'd use lowercase letters to represent variables for lengths. So like the side lengths of a triangle, we'd use a lowercase standard letter. What are those called? Like our alphabet has a special name. I forget what it's called. Huh? Oh, yeah, I don't remember. No, there's something like, it's some kind of like, we have Greek letters, there's like blah 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 letters. But I can't remember what the blah 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 is. Anyways, it doesn't matter. Okay, so we have this formula. What's the important piece for this formula? There is a restriction on it. What is the restriction to using this formula? Yeah, the angle that we have or that we're using has to be in radians. How would this formula change if we had an angle in degrees? Well, I could use the same formula if I just converted my angle measure from degrees back into radians, right? So if I multiply my previous formula for an angle measured in radians by pi over 180, that'll convert this, and we can just say that this is pi r theta over 180. Okay. So if we had an angle measured in degrees, all we're going to do is add on this times pi over 180 to our formula. And by doing that, basically, we're just converting that angle measure into degrees into radians so that it fits with the previous formula. Okay with that idea? Okay, let's do some examples. So if we're asked to solve for x, or solve for s, if r is 1.4 meters and theta is 0.98 radian, which of the two formulas should I use, the first formula or the second formula? The first one, because the angle measure we're given is in radians. And then all I need to do is to fill in my values for r and for theta. And when I type this into my calculator, I get 1.372 meters. Everybody okay with that? What if we're asked to solve for s if r is 3.8 inches and theta is 40 degrees? Which of the two formulas should I use in this case? The second one, that's correct, because we have an angle measure given in degrees. So I'll just plug everything into that formula. And when I type this into my formula, I get about 2.653. Notice here on these example problems, I'm trying to be very careful about when I say is equal to versus is approximately. So I have standard equal signs, and then I also have approximate equal signs. Basically, whenever I did any rounding, I'm going to write the approximate to show you guys that this was a longer decimal that I rounded, versus a straight equal sign, which is, I didn't do any rounding here. That's exactly what it equals. So I'm going to try to be very careful throughout this course using these two symbols of equals and approximately equal. Just FYI, I'd love it if you got into the same habit, although I certainly wouldn't penalize you if you didn't. But if you plan on a career as a mathematician or an engineer or whatever, or even really a scientist, this is a good habit to kind of get into, because there's a big difference between hard equals and approximately equal. Anyways, continuing on, let's do another. So, suppose we want to solve for r if s is 18 and theta is 2.13. Kate, do you have a question? Oh, good question. Yes, this would be in inches. Thank you. Yeah, that does have a unit attached to it. It's an arc length, so the length of that arc is going to be measured in the same unit as the radius was measured in. Good question. Okay, back to C then. What formula should I use for this? The first one. Very good. S is equal to R theta, because we know S and we know theta. So I know that R then is approximately, I do 18 divided by 2.13. Everybody so far so good? And these first three examples were probably, you thought were tremendously easy, and they were, and that's okay. Leone? Yep. Well, we'll see some examples where things might get a little bit more complicated, but I don't think they get any more difficult, if that makes any sense. Like the problem gets longer, like there's more things to do, but none of them get much more complicated. This course obviously is going to get more difficult than what we're doing right now, but I don't think the work today gets tremendously complicated, or I should say difficult. Bye. Okay. So let's say we're asked to find the perimeter of a sector with a central angle of 1.7 radians, cut from a circle with a radius of 5 centimeters. So there's probably a little bit of light unpacking that we should do based on the vocabulary of this question. So there's two words specifically in this question that we should probably review what they mean. So the first thing I'm going to say, or I'm going to ask about is, what does it mean when we're asking for the perimeter? Just really informally, what are we doing if we're trying to find the perimeter of something? What is the perimeter? Good, the distance around the figure. Yes. Everybody agree with that? So we'd add up the lengths of all the edges of the figure, and that would give us the perimeter. Everybody cool with that idea? Okay. When we say sector, what shape is a sector? So a sector is just like a pizza slice. Oops. That is not what I pressed. So when we cut a pizza, and I'm talking about like a round pizza, not one of these stupid like jet square pizzas, we'd end up with a pizza slice that kind of looks like this, right? So a sector is this figure ABC here that's basically just like a slice of pizza. Everybody okay with that idea? So if I want the perimeter of the sector ABC, to do that, I'm going to just find the measure of AB plus the measure of BC plus the measure of arc AC. Everybody okay with that idea? So the measure of AB and BC is easy. How long is AB and BC? 5 centimeters. How did you know that? Yeah, they're both radii of the circle, and we know the radii, or the radius is 5. So each of those is 5. Everybody good with that idea? We still need to find AC, though. How are we going to find AC? What piece of information haven't we used yet? Yeah. So I'm just going to use my formula. S is equal to r theta, because that's going to give me the radius. So I'm going to have 5 times 1.7. When I add that up, I get 18.5 centimeters. Everybody okay with that? So again, at first glance, this didn't look like a question that was just involving using this like S equals R theta formula. But on closer inspection, maybe, oh, it really just, the hard part came down to using that formula to calculate that arc length. Everybody okay with that? One more example from this section, then we'll move on. So suppose that a car has 18-inch diameter tires on it, and if that car is traveling at 15 miles per hour, how many revolutions per second are the tires making? So what quantity are we asked to find in this question? Revolutions per second, right? What kind of a quantity is that? What kind of a quantity is revolutions per second? It's a rate, correct? What word in there indicates to us that this quantity is a rate? Per. Are we given another rate in this problem? Miles per hour. So my goal then is going to be to convert miles per hour into revolutions per second. Everybody okay with that plan? So I'm going to start with 15 miles per 1 hour and do a bunch of conversions to end up in revolutions per second. Everybody okay with that plan? So let's do the easy part first. I'm going to convert hours to seconds because that we all know how to do right away. To convert hours to seconds, what would I first do? convert hours to minutes. So how many minutes are in 1 hour? 60. Should the 60 minutes go in the numerator or the denominator? Denominator. Very good. So we've canceled hours and we're left with minutes. Now let's convert minutes into seconds. How many seconds are in a minute? 60. Should the 60 seconds go in the numerator or denominator? Denominator. So now the minutes cancel and we're left in seconds. So we've done the easy part. What we need to do now is figure out a way to convert miles, a linear distance, into revolutions. So let's think about what a revolution really is. To figure out how far a revolution is, I need to figure out if I have my tire and it spins 1 time, like how far did it go? Everybody okay with that idea? Does anybody know how far that's going to be? What's that? It's not going to be 18 per se. So imagine if I, say, cut my wheel right here at this point, and I unwrapped it, I'd lay the wheel down like this, right? If the wheel is just like that line, I cut it there, and I unfold it and lay it down. This length, then, is the same length as the circumference. Everybody okay with that? So I know that 1 revolution is 1 circumference. And in our case, the radius, we're told the diameter of our tire is 18, so the radius is 9. So our circumference is going to be 18 pi. So you were close there, Allison. And the unit here is inches. So, great. I have now a conversion between a linear distance and a revolution, but the unit I need my length to be in is in inches. Right now it's currently in miles. So let's next convert miles to inches. To do that, I would first convert miles to feet. I know that 1 mile is how many feet? 5,280 is correct. And then I know 1 foot is 12 inches. And then I know that 18 pi inches is 1 revolution. We feel okay there? So to type this into my calculator, again, I'm going to use the fraction command. And I'm just going to type in everything in the numerator. So 15 times 1 times 1 times 5,280 times 12 times 1 over 1 times 60 times 60 times 1 times 1 times 18 pi. Uh-oh. Oh, I sure did. So you guys know you can press second and then the delete key to insert something in so it doesn't type over everything else. You don't have to start all over again. I showed somebody that yesterday and they were like, what? I've been typing it all over the whole time. No, that second delete and allows you to insert a symbol in, which is super useful, especially when you make typos. So, 4.669 revolutions per second. And I guess I should change that from a hard equals to a approximate. Questions about this? So again, maybe a little bit complicated, but nothing was tremendously difficult there, right? The skills that we were doing is just basically converting measurements and calculating a circumference. None of that was terribly, terribly difficult. The problem itself was kind of complicated because there's a lot of steps to it, but not difficult steps, right? On to section 2. So, in section 2, we're going to talk about trig functions of acute angles. To do that, we're going to default back to the part of geometry related to trigonometry that I think every single one of us said that we remembered, which is SOHCAHTOA. Yup, that's what I'm hitting at. So let's say we have this right triangle with angle theta. Which side would we call the opposite side? CB or BC. Which side would we call the adjacent side? BA or AB. And the hypotenuse then is obviously CA. Okay? So if I said sine theta, what is the formula to find sine theta? Opposite over hypotenuse. That's the SOH from SOHCAHTOA. And then how about cosine of theta? How do I find that? Adjacent over hypotenuse. That's the CAH from SOHCAHTOA. And tangent theta is opposite over adjacent. That's the TOA of SOHCAHTOA. So I trust that these 3 trig functions you guys are quite familiar with. There's 3 more trig functions, though, that we're going to care about in this class. Allison? Oh, go ahead. Great. So there's secant, cosecant, and cotangent. These are referred to as the reciprocal trig functions. Yes, Colette? Of course. Because the definition for cosecant is hypotenuse over opposite. The definition for secant is hypotenuse over adjacent. And the definition for cotangent is adjacent over opposite. If we compare those, I notice that the definition of sine and the definition of cosecant are reciprocals. The definition of cosine and the definition of secant are reciprocals. And the definition of tangent and cotangent are reciprocals. So if I know the definition of sine, cosine, and tangent, I know the definitions for cosecant, secant, and cotangent. Everybody okay with that? The trick will be to remember which pair together. The way that I remembered it when I was a high school student was I remembered that no cos go together. So cosine doesn't go with cotangent or cosecant. It goes with secant. And if I knew that, I knew the tangent ones go together, and I could tell that cosecant then went with sine by exclusion, basically. Okay. Let's do some examples to remind us of the kinds of problems we can do with this. So let's find the value of all 6 of our trig functions for this angle theta here. So before we start filling in these trig functions, what do we need to do? Before we can answer this question of the exact values of these trig functions, what do we have to do? Find the hypotenuse. Good. How do I find that hypotenuse? Yeah, I can use the Pythagorean theorem, a squared plus b squared equals c squared. So I get that the square root of 29 is the hypotenuse. Everybody happy with that? So, what is sine theta then? Good. 5 over the square root of 29. Now, are we going to leave our final answer as 5 over the square root of 29? So if you remember when we talked about simplifying things a little bit earlier, you guys asked about rationalizing denominators, and I said, you don't need to worry about it now. I'll let you know when you need to worry about it. This is a situation where we are going to worry about this. If our fraction contains only numbers, like 5 over the square root of 29, I would expect that you rationalize this denominator. And by that, what I mean is that you multiply the top and bottom by the square root of 29, so that I have no radicals in my denominator.
We'll be to the gym for our maths together. Remember, we're going to the gym for math. The teachers would like to be in a prayerful mood as well, so make sure that you're behaving properly. Please get rid of gum and candy from your mouth, and those of you wearing ties, they should be up at your top button. At this time, I'd ask choir members to head to the gym. Leave everything in your classroom right now. Choir members, please head to the gym and sit in the designated seats. 6th grade, could you please head to the gym? And I think inside. And could classes in rooms B1, B2, B3, B4, B5, B6, B7, B8, B9, B10, B11 head to the gym.
Okay, we'll stop here, obviously. Remind me where we left off, and we'll pick up there tomorrow. Okay, guys? You're welcome. Yeah, I did post a homework assignment.